Hello all, welcome to Vishnu's lectures. So in today's concept, we are going to discuss all these concepts like what are tokens, constants, how to declare a variable, size of all data types, ASCII values, format specifiers for all the data types, IEEE 754 standard means how to represent binary for float data. Means if I ask you like write binary for 100, you will write simply. But if I ask you how to write binary for 5.5, how to write? How to write binary or how to represent binary for floating point data? That we will discuss. And similarly, we will discuss what is sine, exponential, and mantissa. Okay, let's go. So first, what are tokens? So what is token? Token is the smallest entity in a program which is meaningful to the compiler. So it's a smallest entity in a program which is meaningful to the compiler, just like comma, semicolon, all the operators like plus, minus, modulus, multiplication, whatever it is, and all the keywords like int, char, float, all these things treated as a token. Okay, next, constants. Actually, we have four types of constants. Okay, that is integer constants, character constants, string constants, real constants. But what is constant? We know very well what is constants. Constants are the fixed values which are unchangeable throughout the program. Getting my point? Constants are unchangeable. Okay. So now, how many constants are there? First, integer constant. What are the integer constants? All the numbers like 5, 10, octal 51, hexadecimal 69. So all these numbers are by default treated as integer constants. Then what is character constants? Second one. So character constants means which is represented in single quotes, which are represented in single quotes that are treated as character constants. Then what is string constants? String constants are represented in double quotes, that is treated as string constants. And real constants. Real constants means floating point data like 5.2, 3.5, 1.2. So that is treated as real constant. Real constants may be float or may be double. By default, real constant is treated as double. By default, integer is treated as all the numbers are treated as integer. Okay. Next, how to declare a variable? How to declare a variable means first you have to write data type and variable name, just like this. Data type, variable name, data type, variable name, data type, variable name, data type, variable name. Okay. So this is the declaration of a variable. Whenever you declare variable, so at runtime, the memory will be allocated for this. For suppose, let's say int x equal to 5. So what happened? What you are thinking? We are thinking that 5 will be stored in X. Of course, you are correct, but you should think like 5 binary will be stored in X. That is correct. Means, first of all, what is the meaning of this statement? Int x equal to 5. Can I split this into two statements? Yes, like int x semicolon x equal to 5. This is the meaning of the above statement. Okay. So first of all, how many bytes allocated for x? It is an integer, so 4 bytes allocated for x. How many bytes? 4 bytes allocated for x. Okay. Now, in x, who is going to be stored? 5 or 5 binary? 5 binary. I already told you that system not understand or CPU not understand the numbers. CPU understands only the binary language. So that's why 5 binary will be stored in this 4 bytes format. So 4 bytes means how many bits? 1 byte equal to 8 bits. So 4 bytes equal to 32 bits. So you have to write the binary of 5 in 32-bit format, 0000, all zeros, 101. This is the binary for number 5. So actually this binary is going to be stored in the X. How many bytes? 4 bytes. How many bits? 32 bits. 0, 1. So all these, if you count all these bits, how many bits are there? 32 bits are there. Like that. For Y, how many bytes allocated? Same, 4 bytes allocated. For CH, how many bytes allocated? For CH, only 1 byte, because it is a character data type. For Z, how many bytes allocated? For Z, 8 bytes, because size of double is 8 bytes, like this. So from this discussion, what you have to know clearly means, you should know that in the variable, binary is going to be stored. In the memory, binary is going to be stored, not the numbers. That is our motto. Okay. Next. Next, very important, ASCII values. So we have some ASCII values, like for capital A, the ASCII value is 65. For capital B, ASCII value is 66. Up to Z. For capital Z, ASCII value is 90, like this. For capital E, 69. ASCII value is 69, like that. So for small a, ASCII value is 97. For small b, 98, like that. Small z, the ASCII value is 122. For numeric, this is for lower case. Small a, small b, small c, these are lower case. Capital A, capital B, capital C, and capital D, all these are uppercase values, right? For numeric, for 0, 48. For character 0, ASCII value is 48. For character 1, ASCII value is 49. For character 2, character means it should be in single code, single quotations, then only it is treated as character. So like that. For 2, ASCII value is 50, like that. And for 9, ASCII value is 57. Just take a screenshot. Okay. So these are the ASCII values. Okay. Next. And there is no ASCII values for special characters. Special characters like hash, star, except this uppercase, lowercase, and numeric, whatever you are watching in your keyboard, remaining all are treated as ASCII values. Sorry, all are treated as special characters. Getting my point? So special characters like what are special characters? Except all these, what we have mentioned here, except all these things, remaining all, whatever we are able to see in the keyboard, all are treated as special characters. Like, what are the special characters? Like plus, is there plus here anywhere? No, so plus is a special character. Hash, star, dot, whatever it is, everything treated as special characters only. Getting my point? Okay, next. Format specifiers. Format specifier for character constant is percentage %C. For 1 byte assigned integer, percentage %HHD. For 1 byte unsigned integer, percentage %HHU. For signed short integer, percentage %HD. For signed integer, percentage %D. For unsigned integer, percentage %U. For signed long integer, percentage %LD. And for percentage %LLD is for used for long signed integer. And similarly, unsigned long int, format specifier is percentage %LU. Percentage %LLU is for unsigned long integer. Okay, these are the format specifiers. And some more format specifiers, like for float percentage %F. For double, percentage %LF. For binary, for printing binary, percentage %B. For octal, percentage O. Hexadecimal, percentage %X. For exponential, percentage %E. And very important point here, by default, all the decimal numbers are treated as signed integer. Okay, now we will discuss this practically also. And second point, by default, real data is treated as double. Okay. Next. So we'll discuss this practically. Means sizes of all the data types we'll discuss now practically. Vi space size dot c. Okay. See. Now listen. Size of 2. What is 2 here? What is 2 here? Integer constant. So size of integer constant is how many bytes? I already told you, by default, all the numbers, all the natural numbers are treated as signed integer. So what is the size of signed integer? 4 bytes. So that what is the size of 2? What is the size of integer constant 2 means 4 bytes. Okay. Similarly, what is the size of character constant? Size of, so whatever represented in single quote, that is stated as character constant, that I already told you. So what is the size of character constant? What is the size of character constant? Tell me. So size of character constant is 4 bytes. Don't think it is 1 byte. Sir, why is the size of character constant is 4 bytes? Why not it is 1 byte? See, whenever you take a character into the variable, consider just like char, or just take some variable like x equal to character constant a. Now tell me, in x, who is going to be stored? A is going to be stored, or a binary going to be stored? Is there any a binary? For ABCD, is there any binary? No. So here, what is the ASCII value for A? The ASCII value for A is 97. Getting my point? So now in X, 97 is going to be stored. Means 97 binary is going to be stored. Getting my point? So in X, A is not going to be stored. Who is ASCII value? What is the ASCII value for small a? 97. So 97 binary is going to be stored in X. So I already told you 97 means which data type? Integer data type. So what is the size of integer? 4 bytes. That's why whenever you are directly writing size of character constant, means it is the meaning of its ASCII value. It represents its ASCII value. So you have to think here size of a. Instead of size of a, you have to think like size of 97, because a ASCII value is 97. So that's why 4 bytes. Getting my point? Next, size of 5.5. Size of 5.5. Now tell me, 5.5 is which data type? Real data type. So real data type may be float, maybe double. Real data type may be float, maybe double. But by default, real data type is double. If you are not mentioning it is float or it is double, so by default it is treated as double only. Then what is the size of 5.5? Now tell me, 5.5 is which data type? Real data type, of course, but which data type by default? So by default it is treated as double. So what is the size of double? 8 bytes. So I'm talking all the sizes based on my compiler. My compiler is 64-bit compiler. The sizes of all the data types may vary from system to system, platform to platform. If it is 32-bit, the result may vary. Okay. Next, size of XYZ. What is XYZ here? Whatever represented in double quotes, that is treated as string. Okay. So number of characters X, Y, Z. So each character occupy 1 byte. 1, 2, 3. And very important point, every string, if you are saying it is a string, means that should be definitely terminated with null character. So what is the null character, sir? This null character represents end of the string. It represents, null character represents end of the string. Okay. So now tell me, what is size of XYZ? Don't think size of XYZ is 3 bytes, because you should consider, if it is string means you should consider null character at last. So then size of XYZ is 4 bytes. Size of XYZ is 4 bytes. Okay, no? So 4 bytes. X is 1 byte, Y is 1 byte, Z is 1 byte, plus null character is 1 more byte. So total 4 bytes. Next, size of character. Size of character is directly 1 byte. Size of short int 2 bytes. Size of integer 4 bytes. Size of long integer 8 bytes. Size of long integer 8 bytes. Size of float 4 bytes. Size of double 8 bytes. Size of long double 16 bytes. Getting my point? See here. So these are the sizes of all the data types. Just compile and execute this. Okay. Just compile this. GCC space size dot c dot slash dot out c 4484124884816. If you want to compare it, just write cat command, cat space size dot c. So now printf size of 2 is 4 bytes. You can compare this. I hope clear this much. Next. Next, what I want to discuss is like, you should not mismatch the format specifier. Means you should use for respective format specifier for respective data type. Like if I take signed short integer, what is the format specifier for signed short integer? Percentage HD. You should not use signed short integer for float data type. Then what happened? The result will be unpredictable. So what I'm trying to convey here is, see here, vi space formt.c hash include stdio.h int main function. So for suppose I'm taking float f equal to, let's say 23.5. If I want to print this data, what format specifier I have to use? Because it is float data, so I have to use percentage f. Then you will get correct output. Printf percentage f comma f. See now, GCC space now, no warning, no error. You will get 23.5. Okay. Now I want to change this. For suppose I am using percentage d. Percentage d we should use for signed integer, but I am using to print float data. Now tell me what happened. Is 23.5 going to print? At least 23 print. See here. Unpredictable output. Getting my point? So for float data, you have to use percentage f only. Should not mismatch the format specifier. But I'm going to discuss one interesting point here. Let's take one more example. That is short int. Let's say short int x equal to, let's take 100. So I'm taking short integer, right? This short integer is which data type? Means signed or unsigned? Signed short int, because if you're not mentioning any modifier, by default it is signed modifier, type modifier, right? So short int x equal to 100, printf percentage d comma x. Am I using correct format specifier or wrong format specifier? Definitely wrong format specifier, because for signed short int I have to use percentage hd. I only told you that you should not use the different format specifier. You have to use respective format specifiers only, right? Now see here, gcc space dot c dot slash a dot out. 100 is printing. Am I using correct correct format specifier? No, I should use percentage hd, but I'm using percentage d, even though I'm getting correct output. Why? This is interesting. Sorry, you only told that you have to use respective format specifier, even though if you are not using correct format specifier, then why sir the output is correct? See here, you should think like this. First of all, whenever you are taking the value short int x equal to 100, now tell me, this x can able to store how many values? How to justify this? This belongs to which data type? Short integer. So if it is short integer, means signed short integer. If it is signed short integer, how many values it can able to store? From -3 to 7,682 plus 3 to 767. Okay. So now this is for signed short integer, which is percentage hd, and percentage d means signed integer. Signed integer means -4 giga to plus 4 giga. Okay. Now see here, whenever you are taking x equal to 100 and printing percentage hd format, so percentage hd is a signed integer, signed short integer, and it can able to print this 100 or not. Means in percentage hd, in this range, this 100 is existing or not? Existing. That's why the 100 can able to print. And one more thing, if I take, don't confuse, if I take percentage d, now what is the meaning of this? 100 is stored in short integer. Now you are printing this 100 in terms of percentage d. Percentage d means signed integer. So in terms of signed integer, which is percentage d, 100 is existing in this range or not? This range is -4 giga to plus 4 giga. So 100 is existing or not? Existing. So in percentage d means -4 giga to plus 4 giga, which is signed integer. 100 is existing or not in this range? Existing. That's why 100 is going to be printed. If you take percentage f, 100 is not existing, and if I take percentage HHD, percentage HHD is for 1 byte, signed integer, 1 byte. Only it will print 1 byte. So 1 byte means 8 bits. So signed means minus 128 to plus 127. 1 byte signed means minus 128 to plus 127. So now 100 is existing in percentage HHD or not? Means percentage HHD is for 1 byte signed integer. Of course, signed short integer. So now, so 1 byte signed short integer means signed means both positive and negative, means the range should be minus 128 to plus 127. This is belongs to percentage HHD, signed short integer, 1 byte signed short integer. Percentage HHD means 1 byte signed short integer. So 100 is existing in this range or not? So you are storing 100 in signed short integer and printing in 1 byte format. In 1 byte format, it is existing or not? Existing. That's why even though format specifier is mismatch, the output is going to be printed. See here. Now what we have to do, let's take more value here. Let's take 129. See, you are printing 129 in terms of percentage HHD. Means percentage HHD means in terms of signed 1 byte signed short integer. So in 1 byte signed short integer, 129 is existing or not existing. See the range minus 128 to plus 127. So 129 is not existing. Then the output will not print. See, minus 127 it is printing. Getting my point? So what is the final conclusion? The final conclusion is whenever you are taking any data, you should use the respective format specifier only. Means for for short integer, means signed short integer, you have to use just percentage HD. Otherwise, you will get unpredictable output. Getting my point? See now, it is printing same. I hope you are clear about this format specifiers. I'm not giving more examples. Whatever the examples I take, same concept only. Getting my point? So, and last and final example I'm taking. If I'm taking short int x equal to 129, percentage LF. Percentage LF is used for double data type. So, you should not print the integer data type in terms of float, the float data type in terms of integer, because that is unpredictable definitely. Getting my point? So what if I take percentage LD? Percentage LD is for long signed integer. In long signed integer, 129 existing or not? Definitely existing. Long signed integer is maybe from minus 8 giga to plus 8 giga, like that, if it is 8 bytes. So 129 existing or not? Existing. So it will be print. Like that you have to think. Okay, na? So final conclusion is you have to use the respective format specifier only. Getting my point? Next, we have to discuss that ASCII values. ASCII.c. Just a minute. stdio.h int main function, and take the value as char ch equal to capital B. Now tell me, what value going to be stored in ch? This point I already told. What value going to be stored in ch? Is B going to be stored in ch? No. What is B ka ASCII value? Capital B ka ASCII value is 66. 66 ka binary in 1 byte format is going to be stored in ch. Sir, why sir 1 byte format? Because how many bytes allocated for ch? Only 1 byte. Because the ch is belongs to character data type. Getting my point? So in ch, 66 binary is going to be stored. Can I say ch is holding 66? Yes, because 66 binary means 66 only. Can I say ch is holding character B? Yes. See here, printf percentage C slash n comma ch. You are printing ch in terms of character. So percentage C is used for character. So if you print percentage C, then what is going to be printed? Of course, B is printed. B is a character. See here. See, B is printed here. But what if I use percentage D here? If I use percentage D here, 66 is going to be printed because B ka ASCII value is 66 and you are printing in integer format. 66. Can I use percentage HHD here? 1 byte means, can I able to print 66 in 1 byte? Yes, because 1 byte value is from -128 to +127. In this range, 66 is existing. You can use percentage HHD also. Getting my point? Okay, now. So what if I take here 100? Is ch able to store 100 or not? First of all, tell me, ch belongs to which data type? Ch belongs to character data type. Signed or unsigned? Signed character. So what is the range for signed character? -128 to +127. This I discussed in previous lectures. So without watching previous lectures, you may confuse. Okay, fine. So this ch belongs to character, that to signed character. So what is the range for signed character? -128 to +127. So this 100 can able to store in ch or not? Of course, can able to store. So if I print this 100 in percentage HHD format, what is the output printed as? 100 only. In integer format you are printing. Percentage HHD means integer. Sir, I want to print it in character format. Okay, you can print. What is the, whose ASCII value is 100? Whose ASCII value is 100? Small d ASCII value is 100. So you are printing 100 in terms of character. So the d, small d is going to be printed. Getting my point or not? See, what I am trying to explain here, the importance of format specifiers in terms of what you are going to print. In terms of percentage C, in terms of character, you are printing this. I hope clear this. Okay. So what is the conclusion? You should use the correct format specifiers. Otherwise, you will experience the unpredictable outputs. Okay. Okay. Next, very important concept. How to write a binary for float data. This is our target now. How to write binary for float data? Means, example, if I ask you write binary for 23.4, if I ask you write binary for 100 or 50 or anything, you may write simply. But if I ask you how to represent binary or how to write the binary for pointers, like not pointers, how to write binary for float data like 23.4, 23.5, 5.5, like that. So how to write? For that, some concept is there that is called IEEE 754 floating point representation. That concept we need to discuss. Okay. So now we need to follow 5 steps to represent the binary for float data. What is step 1? Step 1 is write the binary for integral part first. Means first you have to write binary for 23. In 23.4, which is in integral part and which is fractional part. Integral part is 23 and fractional part is 0.4. 0.4 is nothing but 0.4. Okay. So first write the binary for integral part. First we have to write binary for integral part. Okay. Next, step 2. Write the binary for fractional part. Write the binary for fractional part. What is the fractional part here? 0.4. Fine. Next, third point. Shift the dot towards left after 2. Towards left, you have to shift that dot. Point you have to shift. Towards left, if it is positive data, towards left you have to shift. Towards left to first bit. Towards left you have to shift that point up to first bit, after the first bit. And very important point, that first bit should be 1 only. That first bit should not be 0. That first bit should be 1 only. This you will understand while I'm explaining. Don't worry. And what is step 4? Just remember the steps. How to write the binary for float data. For that, you have to just remember the steps. And what is the step 4? Step 4 is count the number of bits shifted. So what is so you are shifting that dot right towards left. So just count the number of bits shifted. Okay. Next, step 5, simply represent the binary in sine, exponential and mantissa format. Getting my point? This I will discuss. Don't worry. Just remember the steps. So now I'm writing the binary for 23.4. So 23.4. Let's say this is a float data. Float means how many bytes? 4 bytes. Okay. So what is step 1? How to write binary for 23.4? What is step 1? Step 1 is write the binary for integral part first. What is the integral part here? 23. So 23 binary is how to write? 1, 2, 4, 8, 16, 16, 1, 16 plus 4, 20, 20 plus 2, 22, 1, 23, 0. So this is the binary for 23. Step 1 completed. Put dot here. Now what is step 2? So step 1 completed. Now step 2. What is step 2? Step 2 is write binary for 0.4, means 0.4. How to write binary for 0.4? So binary means you have to multiply with 2. Binary means 2. So step 2 is 0.4. Take this into 2. Same rule applied for any number. Okay. 0.4 into 2, which is equal to 0.8. Take 0. Next, take this 0.8 into 2, which is 8 to 0 16, means 1.6. Take 1. Next, from this extract 0.6. 0.6 into 2, which is 1.2. Take 1. Next, 0.2 into 2, which is equal to 0.4. Take 0. Next again 0.4 into 2. If you observe, again the 0.4 is repeating here. Means even though if you do, again it will come 0.8 into 2. Same will be repeated. Same values will be repeated again and again. So it should be like 0 1 1 0, again 0 1 1 0, again 0 1 1 0, again 0 1 1 0, like that. So simply keep this as a bar, means 0 1 1 0 bar. It means the 0 1 1 0 is repeating every time. So dot 0 1 1 0 bar. Now tell me, how many steps completed now? 2 steps are completed. What is third step? What is third step? See here. Shift the dot towards left after to the first bit. That first bit should be 1. Means shift this dot. So if I shift this dot towards left to the first bit, is the first bit is 1? Yes. If it is 0, you have to consider this. If it is 1, again you have to shift this dot to the left after first bit position, means to here you have to shift. Is this 1? Yes. So you have to shift here. How many bits you have to cross for this? So you have to shift this 1, 2, 3, 4 bits you have to cross. Okay. After shifting this dot towards its first bit position, if you shift like this, what is the result? Result should be 1 dot 0 1 1 1 0 1 1 0. This is the result. Okay. Step 3 completed. What is the step 4? Step 4 is count the number of bits shifted. 1, 2, 3, 4. So count equal to 4. This is useful later. Why, sir? What is the use of count? This is useful later, I will tell. Okay. So clear, I think. Right? Okay. Now, what is next step? Represent this in sign exponential mantissa. So there is a concept called sign exponential mantissa. So here, so represent in sign exponential mantissa. Sign bit. This sign bit is 1 bit. This sign bit represent positive or negative data. So tell me, whatever the data we have taken, what is the data we have taken? 23.4, right? This 23.4 is positive or negative data? Positive data. If it is positive data, the sign bit will be 0. If it is negative data, the sign bit will be 1. Getting my point? So this is the 0. Next, exponential. Exponential is 8 bits. Exponential is 8 bits. So what is 8 bits maximum value? 8 bit maximum value is 127. 127 plus number of 127 is fixed. For every number you have to add 127 plus number of bits shifted. Don't confuse. 127 is fixed for every number. Whatever the data you have taken, 127 is fixed. 127 plus number of bits shifted. How many bits shifted? I already written count now above. The count is 4. 127 plus 4. What is the value? 127 plus 4 is 131. So you have to write 131 binary. This is 1 bit. This is 8 bits. So 131 binary. 131 binary should be like 128 plus 3, right? So 1 plus 2 plus 4, 8, 16, 32, 64, 128. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is the exponential. So float means how many bytes? I already told you. 4 bytes. 4 bytes means how many bits? 32 bits. So already 8 bits and 1 bit done. And how many bits left here? 23 bits. This 23 bits is the mantissa part. This is the mantissa part. After shifting one, this remaining part is there, na? This is the mantissa part. What is the mantissa part here? 0. Write this mantissa part as it is. 0, 111, 0, 110. How many bits? 4, 4, 8. What about remaining? This 0, 110 is repeating. So write it 0, 110, 0, 110 like this. So up to how many times you have to write? So it should be total 23 bits. Up to you are reaching to 23 bit, you have to write it. 1, 4, 8, 12, 16, 0, 110, 20, 0, 11, 23. So this is the binary for 23.4. Getting my point or not? So in memory, this is the value going to be stored. But in memory, there is no concept of sign, exponential, mantissa. This is mantissa part. Just for binary representation it is. But in memory, it will be stored like this. 0, as it is, I am writing 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 111, 0, 110, 0, 110, 0, 110, 0, 110, 0, 11. This is the binary for 23.4. Getting my point? So same rule applicable for double also. But what is the difference in double? Same, everything is same, but the size of double is different, right? For that sign bit is 1 only. Sign bit is 1 bit only. So it represents positive or negative. If you are taking negative data, then sign bit will be 1. If you are taking positive data, then sign bit will be 0. And next, exponential. Exponential will be 11 bits. 11 bits. So add 1023 plus number of bits shifted count. Same story like previous how we discussed, same like that, but number of bits shifted count should be added to 1023. For suppose the number of bits shifted is 2, then 1023 plus 2, 1025. So you have to write 1025 binary in 11 bits format. 1025 binary you have to write here. And as it is, after dot 10 like this, whatever the result you will get, this is treated as mantissa part. This mantissa part, I'm telling this in double case. If you are dealing with double, so how to write binary for double data means same for double data also, sign, exponential, mantissa, but the size of double is different. This is 1 bit, 11 bits, and this is about 53 bits. 52 bits. 52 plus 12. Yes, 52 bits. This 52 bits is mantissa part. Getting my point? Yes or no? Okay, now what if the number is like this, like 20.5? 20.5. How to write binary for 20.5? Let's say 20.5 is double. We'll see in next page, same thing. Write binary for 20.5. Let's say it is double. Okay. So this is double. This is not float. Consider this is double. So now whatever it is, what are the steps? What is step 1? Step 1 is write the binary for decimal part first. So write the binary for 20 first. How to write binary? Step 1, 1, 2, 4, 8, 16. So 16, 32. Nearest number is 16. So I'm writing binary for 20 first. 16 plus 4, 20. Remaining all are zeros. Point. Now what is step 2? Write binary for fractional part. How to write 0. This is second step. 0.5 into 2, which is equal to 1.0, take 1 here. Next, 0.0 into 2. So 0.0 into anything is 0 only. So take 0. So again 0.0 comes, 0 comes. So same. So again. This is not recurring. This is not recurring. So remaining all are zeros directly. So 0.10 is the answer. And zeros are coming. So now 2 steps are done. What is third step? You have to shift this dot towards left to the starting first position after the first position. So for that, how many bits we need to shift? 4 bits. So after shifting, what is the result? 1.0100, 1.010010, right? So count number of bits shifted is 4. Okay. Now represented this in sine exponential mantissa, but the size will be different because the 20.5 I am treating this as a double. So how to write binary for 20.5? First sine bit. Sine bit is 0 or 1. So this is negative or positive, this data positive. So this will be 0. Next exponential part. So in exponential part, how many bits? 11 bits. In float, it is 8 bits. In double, it is 11 bits, exponential part. So what is the maximum 11 bit values? 1023. This is fixed. 1023 plus number of bits shifted 4. So 1023 means plus 4 means 1027. So you have to write binary for 1027 here. Next, here mantissa part. What is the mantissa part? This is the mantissa part. So write this mantissa part here in how many bits format? 52 bits format. So 0, 1, 0, 0, 1, 0. Whatever remaining all are zeros only, not recurring. This is so how many bits I have to write? Total here mantissa part 52 bits. When you reach to 52 bits, just stop it. Okay. Now here in exponential part, what I have to do? Write 1023 plus 4 means 1027 binary. What is 1027 binary? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. 1024 plus 4. Remaining all are zeros. 256, 512. So if you count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits, right? So 1, how many zeros? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 100. Yes. Now this is the binary for 20.5 in 8 bytes format, means in double format. If it is 20.5, if it is float, then here 8 bits only, here 23 bits. I hope clear. So in memory, what is going to be stored in memory actually? In memory, don't think that in memory there is a sine exponential mantissa. No, in memory there is no this type of divisions. Directly this binary will be stored like this: 0, 1, 1, 2, 3, 4, 5, 6, 7, 100. Next to this mantissa part, 0, 1, 0, 0, 1. Remaining all are zeros. This is the binary for 20.5 in double format. Okay. So in upcoming class, we will discuss about typecasting. This is very important. In data types, typecasting concept is very important. We'll discuss what is typecasting with practical examples. Okay. I hope you are clear with this. Thank you.